All right, happy Tuesday. So today we're going to finish off chapter 5. That's the trapezoidal rule and Simpson's rule. What we're going to do is kind of go back to the concepts of the rectangular approximation method and the geometric figures to approximate the area under the curve. The reason why we're going to go back to that is that in real world situations, sometimes there isn't a model that would represent what's going on, meaning there isn't an equation, there isn't some sort of function that we can say that, yeah, this is x squared and this is the square root of x. Take the antiderivative and go from there. In your homework, you're going to have two different situations. One is going to be to approximate the it's going to be the area and then the volume and then the quantity of fish in a pond. And so you're going to have a weird looking pond that we're going to have to use the trapezoidal rule to approximate the area, the surface area of the pond. Then the uniform depth, the problem is going to assume it has, so we can figure out the volume, and then the number of fish that would fit inside that pond, which would then correspond to the number of fishing licenses we could allow in order to guarantee that we still have a certain number of fish every single season, things like that. So the Simpson's rule and the trapezoidal rule will help us make those measurements. The second problem is going to be dealing with a solar powered car, and again, finding some measurements involved, which will help us figure out. And the second question, which I didn't include, is to the dimensions of like the gas tank and other things like that. So we would need Simpson's rule to approximate that. So there isn't a nice model that we can just take the antiderivative of. And now the trapezoidal rule and the Simpson's rule are going to be more exact ways of approximating the area under the curve instead of just blocky rectangles. So here we go. The trapezoidal rule. It's going to use trapezoids to approximate the area under any curve. Now, to keep in mind, the area of a trapezoid is the sum of the two bases times the height divided by 2. And so if I have this curve of y equals x squared, and I wanted to know from 1 to 2 what the area under this curve is, this one's pretty easy to do using antiderivatives and a definite integral from 1 to 2. But it's pretty easy, so that's why I'm also using it as an example. So here we go. I'm going to have 1, 2, 3, 4 trapezoids. And I am going to break them up so that they have an even uniform width. So if I'm going from 1 to 2, that means I increased by a quarter each time. So the first base of my first trapezoid is 1, and the second base of my first trapezoid is 5/4. Then when I move on to the second trapezoid, notice how it shares the same base as trapezoid 1 because they're touching, and then it has the base of 3/2. Trapezoid 3 shares the same base as trapezoid 2, then it has 7/4. The fourth trapezoid shares the same base as trapezoid 3, and then has its own base to finish off my shaded region. So I use 1 and I use 2 just once, but all the other bases I have to use twice because they overlap, and that's where they connect from one trapezoid to the other. So each trapezoid, its calculations would look like this. So it would be 1 squared, and it's 1 squared because, again, if I'm looking for the height or the length of this base, it would be touching the curve when x equals 1. Well, if x is 1, I then plug it in to find my y value, so that's why it's 1 squared and 5/4 squared. So these would be the height of each trapezoid. I'd add them together. I would take a quarter of it, and then I would take half of that. Now, notice I'm not doing the calculations out yet because I want to show you something. So I use this once, I use this once, I use that one again, I use this one again, I use that one again, and then this one I'm only using once. So what I want to do is I want to rewrite the sum of these 4 trapezoids into a nice formula so that I don't have to do any extra work. So here's what I am suggesting. Well, if I am using each of these 3 interior bases twice, what if I wrote them down once, but gave them a multiplier of 2? So then when I square 5/4, I just go ahead and double that, and I'm just dealing with one fraction. I'm also going to take half of 1/4 so that I don't have these 2 division quantities. So half of 1/4 gives me 1/8. And when I go through and I square each quantity, I square each of them, and then I double my 3 middle ones, find some common denominators, simplify, simplify, and I get about 2.34. Now, that is using the trapezoidal rule. If I want to check with antiderivatives to see how exact my answer is, or how accurate, I guess I should say, the antiderivative of x squared is 1/3 x cubed. I evaluate it from 1 to 2, and I get 2.3 repeating, which is pretty darn close to my approximation using these trapezoids. So just to show you how close they are in answers. So here is the trapezoidal rule. In a nice condensed package, the trapezoidal rule says that if you take the height, which is the spacing of each trapezoid, because remember the height is from the lowest point to the highest point. So if you imagine we take these trapezoids and turn them on their side, the height is the even interval. The reason why we made this the height and not that the height is if I want to make a uniform value of the same heights, I can't make it those vertical heights because they change each time and the formula wouldn't work. The formula only works is if every trapezoid has the same height. So it only works is if we turn the trapezoids on their side, so the bases are going horizontal and the height is vertical. So that's how we kind of have to do this in order for this to work. Otherwise, you are going to have to calculate each trapezoid out your own way. So the height divided by 2, and then this says you take the first base, which was 1 in the example, plus 2 times the length of the second base, plus 2 times the length of the third, plus, and you keep doing that for every interior base up until you get the base right before the last one. You still double that, and then whatever one you conclude at, you have a multiplier of 1. So in a nutshell, in the simplest terms, the coefficients, the multipliers, will start and end at 1, and every other trapezoid height or base length in between will be having a multiplier of 2. You can have any number of trapezoids you'd like. You can have even and odd numbers. It doesn't matter. It's whatever best approximates your function. Now, Simpson's rule is under a parabolic arc. So if you imagine that this is going to be going kind of like a trapezoid, but then the top is going to be more curved, so it can really fit inside those nooks and crannies of a curved shape. Now, Simpson's rule can be developed the same way as the trapezoidal rule, but it's not as easy to explain. If we were in class, we'd explore it a little bit, but I don't want to waste your time. So I am going to give you the mathematical definition of Simpson's rule. Instead of the height divided by 2, it's the height divided by 3. And the pattern for the Simpson's rule is the first base, so the first vertical line is going to have a multiplier of 1. And then the second base is going to have a multiplier of 4. Then the third base will have a multiplier of 2. Then 4, 2, 4, 2, 4, 2, 4, 2. It's going to keep going back and forth, back and forth, back and forth. And then the last term that gets multiplied, it will have to end with a 4 and then a multiplier of 1. So there's this little warning here. You must always be partitioned or broken up into an even number of subintervals of equal length. Equal length, so they all have the same height, and even so that this pattern holds true. If you had, say, 4 subintervals, it would go multiplier of 1, 4, 4, 1, and then you'd be done. If you had 5, that would be 1, 4, 2, 4, 1, 3, 4, 5. So we have to be careful about the even numbers there. Hold up. I just want to double check to make sure that I wrote this right. Yes, I did. Okay, I was starting to second guess myself. But anyway, so we have to have an even number of sub-intervals. All right, so I did the example using the trapezoidal rule. So here's just an example of how we would use Simpson's rule, approximating this 5x to the fourth from 0 to 2. So from 0 to 2, I decided to break this up evenly into 1, 2, 3, 4 sub-intervals, which means that my height is 1/2. So I would be having a first base of 0, my second base of 1/2, my third base of 1, my fourth base of 3/2, and my fifth base of 2. This is where I was getting confused. 4 intervals gives me 5 vertical lines. So 5 intervals would give me an even number of lines and the pattern wouldn't hold. That was my hesitation. Anyway, so my height is 1/2 divided by 3, that's 1/6. And so I plugged in my first value, so 0 into the 5x to the fourths. I plugged in 1/2 into 5x to the fourths times 4. I plugged in 1 into 5x to the fourths times 2 times 4 times 1. Combine it all together, and I get 32.1. Now, just to check with antiderivatives, I take the antiderivative of 5x to the fourth, that's x to the fifth. I evaluated at 0 and at 2. I just wrote addition here, but that is not addition. That was sloppiness. I apologize. This should be, as we know, subtraction. And so it didn't matter, obviously, because it was 0, but the answer would have been 32. So pretty close with the approximations. So your homework tonight is just going to be using the trapezoidal rule for one problem and the Simpson's rule for one problem. We'll see how it goes, and we will go from there. Good luck. I'll be in the Zoom if you need anything.